For my constant velocity experiment, I chose to observe a penny rolling across a table. Let's set up the experiment by looking at how I set up the coordinate system when I was working with this data in Tracker. You can see in the image here that I set up the coordinate system so that the initial position of the penny was at the origin and the motion of the penny was along the positive x-axis. I could have set this up any direction I would have really wanted and we would have gotten the same ultimate results out, but this is really the simplest way to set it up. It's a nice, simple, one-dimensional motion. So let's take a look at the actual motion itself, and I'm going to run the video twice. It's only about a second. It goes by pretty quick. So there's the penny moving. What are the forces involved? Well, let's take a look at, we've got a velocity here. This is hopefully a constant velocity. And the forces that are in play that are going to affect that velocity are the other four vectors that we see in this drawing. So we've got the force of gravity and the force of the table pushing up on the penny. Hopefully those are going to cancel each other out because we really want this to be a zero net force situation. There are two forces in the negative x direction. Those are due to any frictional component and any air resistance. But we're hopefully going to be able to assume that those are zero. Since this is a very hard penny on a very hard table, friction should be pretty minimal. Likewise, because the penny is very narrow, very small cross section, as it's traveling through the air, there shouldn't be a lot of air resistance for us to deal with. Let's take a look at setting up our model. So first of all, we've got the mass of the penny. If this is a net force equals zero situation, the mass really isn't important, but we should record it just so that we know it's there. If we look at the initial conditions, again, I said the penny was at the origin, was at 0, 0, 0 for the x vector at the beginning of the experiment, and time was 0. Letting that first frame advance, the penny has moved a small amount. There's the new x1 vector, and the time has advanced a small amount. So we can use that to figure out the initial velocity of the penny, and here we see that the initial velocity of the penny was just over 1 meter per second. Now that we've got that initial velocity figured out, we can go back and look at working through the velocity as time passes. We've got our Newton's second law set up. We can start looking at the velocity change with time. So the final velocity is the initial velocity plus net force over mass times delta t. Again, we've got what hopefully is a zero net force. And if we've got zero net force, the velocity should be constant. So if the net force is 0, it gets rid of that whole second term. If we now look at the position vector, we can get the position vector by taking the initial position and adjusting that up using the average constant velocity, or the constant velocity in this case, times delta t. And here we also see the way that these are formatted as definition statements in Python. Once all the variables were changed and all the code was adjusted in Python, could run the model, and you see the model output looks pretty good. There's what the penny looked like. It moved in the positive x direction for a certain amount, and the model velocity is constant, so we've got a nice graph of constant velocity. Now for the important part of the experiment, how well does the model fit the data that we observe? Here we've got the result, the graph, after I input everything and created this. So we've got the observed data from Tracker as the dots, and we've got the model as the green line that came out of Python. And we can see that the observed data is really matching up very, very well with the model. That tells us that we really were observing something that was essentially constant velocity. We really were observing something that was essentially a zero net force situation. It also means that our assumptions were good. Those assumptions that drag and friction were negligible seem to be valid assumptions for this case. Now you can notice as you look at this graph that as the time moves on, we do see a deviation. There must have been something going on here that had actually increased the velocity. There must have been some force present that made this really not a net force of 0. The most likely culprit here was that the table wasn't exactly level. It was maybe sloping down a little bit, so the force of gravity wasn't quite exactly balanced out by the force of the table pushing up, and we got a very, very slight acceleration. The model looks like it's pretty reliable, and even though there is a small deviation, I think that this shows that the model is reliable and should be useful for predicting the position of this penny if I were to roll it in exactly the same way across the table once again.